In this video, we are going to see power converters for EV charging. So when we see that electric vehicle powertrain, right? When we see electric vehicle powertrain, first things comes to our mind is the power supply. So basically when we talk about power supply, it can be a single phase, that is 230 volts 50 hertz, or it can be three phase, that is 440 volts 50 hertz, right? So what happened here is it is connected to my charging circuit, right? It is connected to my charging circuit, and this charging circuit is further connected to my battery, right? This is my battery, and this will be connected to my electric drives. Okay, this is connected to my electric drives, and then this will be connected to my induction motors. And what we use here is, like, this is my storage, and storage mostly we use my lithium ion batteries, and battery chemically stored, and it's higher energy density. And what happened here is we also use one capacitor here. This is my super capacitor, right? So super capacitor cannot change electrical energy to other form, only stored in electrical charges. So basically why we use here super capacitor is that where braking is frequent, super capacitor is recommended, right? And better life in terms of charging discharging also happen when we use super capacitors. After that, there comes my fuel cell based electric vehicle, right? This was electric vehicle powertrain. Now comes my fuel cell based electric vehicle. So instead of electrical supply, we feed fuel, like. So now today what happened here is India is growing towards hydrogen based fuel. Earlier it was we were using the electric vehicle charging with from solar PV panels, but today from seeing the shortage of electricity, like electricity getting short because of charging of electric vehicles on the roads, nearby charging stations. So that's why India is going towards hydrogen based. So that is a fuel cell based electric vehicle charging. Here it is hydrogen. Now so this is my hydrogen, and this is my fuel cell, right? This is my fuel cell, and here it will give me 1.5 volts. So series parallel connection it will be there for getting the higher voltage. Now this is my DC. Now DC to DC conversion would be there. After that, there will be one storage box for storing that which is being generated, and after that again the driver would be there, and again the induction machine would be there, induction motor will be there. As fuel cell cannot take power in the reverse direction, hence storage is needed, right? Then comes example for that. So let's see one example. Let's consider we are having 230 volts 50 hertz power supply, right? This is my AC power. So this AC power will be first converted to AC to DC using AC to DC conversion, like AC to DC conversion. We will have here 380 volts to 400 volts DC power. Then here one capacitor will connect. This is my big electrolytic capacitor, right? Then this DC would be converted back to the DC, and then it will be used to charge the battery. Now why I am using again DC to DC conversion, this DC conversion, why I am using, because I am already getting the DC here. I'm converting my 230 volts to 380 to 400 volts. Why I am using the DC to DC conversion? First of all, it will provide me isolation, right? Then second part will come on control. It will provide me control operation. Like if I talk about isolation, DC high frequency AC, and it will rectify to DC back. And this battery which we are using here is lead acid battery, right? Lead acid battery. If chopper is used, if this is used, we will use lead acid battery here. Its rating can be 36 volts to 48 volts here. And here, this is my chopper. This is my buck chopper, non-isolated, right? Buck chopper, because 400 volts, if you consider this one, it is converting to 48 volts, and this will be done by buck job, voltage buck. Next things comes about is buck converter. Right, the buck converter, if we talk about is, first of all, let's memorize the circuit. Right, we know that buck converter looks something like this. Buck converter looks something like this, right? There is one power source like VG, there is one diode D, there is inductor, capacitor, and there is one load that is connected on the output side. Now, this battery, we need some battery of electric vehicle we need to charge, which is 36 volts battery, right? And its power rating is 2 kilowatt power rating, the battery which we need to charge here. From that, we will find the resistor, we will get some resistor, we will find that. So we will connect here some R value that will be according to our this rating. Okay, so what we are doing here is, we know that this will be 400 volts, right? This is my DC. What we are doing here is, we are converting my 230 volt supply to 400 volts, and that 400 volts will be reduced to 350 volts, right? So because there is some fluctuation would be there, right? So if fluctuation will be there, it will reduce the DC supply. So what will happen is, if I use my lithium ion batteries, there is, and that is not even controlled, right? If that is not even controlled, that battery will be in danger. Now for that thing, we need our steady state analysis. For designing of circuit elements, we require our steady state analysis of the system. Now buck converter, we will see. Okay, so buck converter, we already know that this is my buck converter. If I talk about my duty cycle, so duty cycle will be output voltage by input voltage, V0 upon Vg. So if I see the circuit of this, like waveform of this, there is this switch SW. If the switch is on, and after some interval it will be off. So when the switch will be on, what happen here is, inductor will start charging, and then it will try to discharge. In this fashion it will work, charging of inductor. So if we put here, this is my VL and this is my, let's consider this is my V0. So voltage sec balance if we apply, like if the switch is on, what voltage we'll get here? If switch is on, we'll get minus Vg plus VL plus V0 equal to 0, and VL will be equal to Vg minus V0. And switch will be off, what voltage we'll get here? It's VL plus V0. Here we'll get VL is equal to minus V0. In this fashion, like Vg minus V0 is equal to, when the switch is on, means dt minus V0, 1 minus dt equal to 0. In this fashion, if we calculate, we will get V0 is equal to d times Vg. That is voltage sec balance. Now what we'll do here is, we will see the boost converter, basic boost converter, right? So we already know that the boost converter looks something like this. We know, let's consider the voltage across the inductor is VL, and here we will put some input voltage, that is DC voltage Vg, current flowing, that is Ig. This is my switch, just 1 minute. This is my switch. Here comes my diode, here comes my capacitor, and here comes my resistor R. Now let's consider when the switch is on. When this switch will be on, what happen here is minus Vg plus VL. If I consider voltage here as V0 is plus V0 equal to 0, VL will be equal to Vg minus V0. And when switch will be off, what it will be voltage? If switch will be off, its switch will be on, I have just written it wrong. V0 will not come into picture, right? So I'll just delete it and I will just write it as minus Vg plus VL equal to 0, and here it will equal to just Vg, and here because output voltage will not come into picture. The switch will be closed, it will be minus Vg plus VL plus V0 equal to 0, and VL will be equal to Vg minus V0. In a similar fashion, if we carry out our voltage sec balance equation, we will get V0 by Vg is equal to 1 upon 1 minus d, right? Now what we need to see here is, we already got the buck converter and boost converter, right? So with voltage sec balance, we will get this equations from previous case also. Now we can also apply current sec balance. We will get the equation with the currents, right? Now we need to see that we know that you can also operate these parts in the discontinuous conduction mode also, right? In PFC we will see the boost converter mainly, like this is my boost converter. In PFC we will see mostly the boost converter. When the boost, that part will come, I will explain further. Now let's see resonant converter. Okay, whenever we talk about the resonance converter, okay, I'll just write, whenever we talk about the resonance converter, there is one wave which comes into picture so many times. We have already seen these wave in circuit, in the circuit and network analysis subject, as well as signal and system subject, and we have calculated the Fourier of that part, right? So if you talk about the Fourier of this wave, and if the time period is t/2 and here it is t, we know that what we will get Fourier from here is, we can easily find out. So when we try to figure out, we'll get here, if this is my voltage, right? So the equation for the voltage we will get from here is 4 V0 upon pi summation of 1 by n sin n omega t will get. We can easily find out from our basics of the system. Now let's try something new, right? Let's take this part to our normal system with rectifier and inverter part. So if I see my rectifier, right, if I see my rectifier, it looks something like this, right? Here will be my AC will be fed here. This is my R0, this is my V0. V0 will be come here. Here AC will fed. Now we know here the current would be sinusoidal. Let current would be sinusoidal. If current would be sinusoidal, and here we know that voltage would be DC. Here is DC voltage. DC voltage means it is fixed. It's fixed. Now the voltage here would be the square wave. The voltage here will be square wave, and this is my V0, right? So we already know that from Fourier we know that V is equal to the above part which we already written. This part, right? This part, V is equal to this, right? Where n here is equal to 1, 3, 5, 7 and so on. Now the current here I is what? I1 sine of omega t. So if I need to calculate the power, we will get V into I by 2. And what is my V here? What is my V here? I know V is 4 V0 upon pi. I is what? Fundamental component, I1 by 2, right? So we can find here is 2 V0 I1 by pi. This is my fundamental component. If two different frequency would be there, then we know that there will be no active power flow, because when it will multiply by each other, it will result into zero active power. That's why for third harmonic, the power for the third harmonic would be 0, because we have fundamental here, right? One here. So that's why the power for the third harmonic component would be 0 in that case. Now if you see that the output for rectifier, we already know that here current will feed, and here we will get in this fashion my current, output current. This is my I0 and this is my I1. So from here we can find that I0 will be equal to 2 I1 by pi, right? So we know that if we just find out that what is my RE, means if this R0 will be shifted to this input side, what, and it will be RE. So from power balance we can find this RE, and that RE would result into 8 by pi square into R0. How? Okay, with power balance what we can write here is, okay, instead of power balance we can also use like RE will be equal to what? V1 by I1, the fundamental component. We know that the fundamental component is 4 V naught upon pi for V1, and I1 would be equal to pi by 2 of I naught, because Re we need to write in terms of I naught and V naught. From here we can find the I1 value in terms of I naught, and from here we can find out the value of V1 in terms of V naught. From here we can find out that it's 8 by pi square into R naught. So one more question I would like to ask is, why we are using here the capacitive filter? Just think. Okay, in this case we are using the input as a current source, right? Because this is my current waveform. So input would be current source. Input is current source. When the input is current source, right, then the output must be the voltage source. That's why we are using the capacitive filter. Now if we consider in the next case, what I will do here is rectifier only. I am using my rectifier. I am using input as voltage source. This is my voltage for, and here my current would be this. This is my current I. Now this is, I'll just draw it. So this is my AC here, and here there will be 1, because my voltage here is, this is my voltage source, so here it should be a current source. Here it should be a current source. This is my V naught, this is my L, this is my C, right? So the voltage which will appear here is something like this. We already know. So I can write this as V naught is equal to 2 V1 by pi, and here the I we can write here is 4 I naught upon pi. That is fundamental. So Re we can write here is V1 upon I1, which will be equal to like pi by 2 of V naught, and here I1 will be 4 I naught upon pi, which we can calculate here is, we will get pi square by 8 into R naught. This is my R equivalent. Now what we can do here is, we can just substitute this part with the part as like this. V is equal to V1 sine omega t with the equivalent resistance, that is R equivalent, and in the previous case we can write here is as current source with equivalent of R equivalent of the previous case, and these values are just opposites. Here we are getting the pi square, here we are getting the pi square by 8 into R naught, and in the previous case we got 8 by pi square into R naught. This is the main difference when we are using the equivalent circuit, right? Now we can also use the inverter, we can also find something for inverter circuit also, but we can see it later on, because it will be required, then only we will see that part. Now there is one more point, like series resonant converter. Okay, there is one term, there is one converter, that is series resonant converter. Okay, we will see that series resonant converter. I'll just show how it looks, right, so that we can figure out how it is formed. So here this is my circuit for full bridge voltage source inverter. Here I am drawing. So this part is my VG, right? Here I can draw the diodes also. Sorry for the figure, bad figure. Here is my LR, here is my CR, and this one here would be my rectifier part. This will be my rectifier, right? Here it will be my capacitor, and here would be my R, the resistor. My capacitor, this is my resistor. So this is my passive diodes, this is my voltage source inverter, and this is my series resonant converter, because here I am using my series LC circuit. Right. Now I can use here galvanic isolation also. Like I can isolate the inverter part with the rectifier part. So how it will look like? Let's see. Let me rub this part. Let me cut this part from here, and here I'll put one transformer. This part will give me galvanic isolation. Now we know that we can draw here equivalent circuit of resonance circuit. This part is my equivalent circuit of resonance circuit. RL, C, and this small inductor transformer part. Otherwise we can do here one thing is, we can refer this R part to the primary, we already know. So here we can write here is this L part, this is LR, this is CR, and here what we refer here is R equivalent RE. And here we can find the equivalent impedance of the primary part. If we see the magnitude versus frequency plot of this curve, we know that we will get the magnitude versus frequency plot something like this. Something like this we will get. This is F0, this is Fs. This is magnitude of G of j omega. We know that here the first part will be the passive elements, like L and C would be big value, and that's why it is a leading, and here it is a lagging power factor at inverter output. Right. Now we will see that